This video is related to the Advance 4 Learning Unit of Storing and Retrieving Data educational module. Hadoop is an open-source project that includes various modules that were independently developed over time to add various types of functionality to its core capabilities. By default, Hadoop assumes a trusted environment. As Hadoop has matured, corporations are of course concerned with the security of sensitive business data that they're increasingly storing in Hadoop-based environments. Unlike in the case of a regular database, in Hadoop there's no central authentication server or mechanism. If users can manage to access the server running the name node and have appropriate permissions on the Hadoop binaries, they can potentially read data they weren't authorized to read and even delete that data. There are no role-based access control, object-level or other granular authentication features in Hadoop. Since you store data in multiple data nodes, each of them is a potential entry point for an attacker, and you must secure all the nodes in a cluster. In order to encrypt data flowing between clients and the data nodes, you must use Kerberos or a simple authentication and security layer (SASL) framework. Communication between the data nodes and the name node also needs to be protected. Encryption is an important requirement for protecting sensitive data. Lack of encryption at rest and encryption of in-flight data means that inter-node communications can be intercepted, and private information stored on disk can be accessed. When Hadoop security is enabled, it requires users to authenticate, using Kerberos, in order to read and write data in HDFS or to submit and manage MapReduce jobs. In addition, all Hadoop services authenticate with each other using Kerberos. Hadoop security involves three main concepts: authentication, authorization, and auditing. The best and accepted way to provide authentication for Hadoop is through Kerberos security. Kerberos provides strong authentication of users and services that work with a Hadoop cluster. Authorization, which determines who can access a Hadoop cluster's data, is a key security concern in any environment. You use access control lists, ACLs, to configure authorization. Apache Sentry lets you configure strong, fine-grained authentication for your data. Auditing is the tracking of activity within the cluster and can include both user and administrative activity. Encrypting data in transit via the network and data at rest, on disk storage, is extremely important, especially when you're dealing with what's known as personally identifiable information. Hadoop administrators need to learn how to put in place authentication, authorization, and accounting policies for accessing and using data stored in the Hadoop clusters, as well as to secure the data in transit and at rest. Securing Hadoop not only involves securing access to Hadoop and securing the stored data itself, data at rest, but also the whole range of security that all IT operations use, such as network security and operating system security. Some general principles that underlie enterprise security in a Hadoop environment will be briefly discussed. Ideally, a Hadoop cluster should be in its own network segment, separated from the rest of the IT environment with appropriate firewalls, as well as security measures such as intrusion detection and intrusion protection systems. It's common practice to configure a secured VLAN for a Hadoop cluster and limit connections to those initiated from the gateway or edge servers only. In general, the network firewalls should permit FTP traffic from a set of FTP servers to the edge nodes. They should also allow the worker nodes to connect to the database servers to send and receive data over specific ports. Ingest mechanisms such as Apache Flume should be able to access log events from web servers over specific ports. Depending on how clients are allowed to access your cluster, you need to set up the appropriate network firewall policies between the applications and the Hadoop cluster, as well as between the applications and users. Authentication answers the question, who are you? Traditional strong authentication methods include Kerberos, Lightweight Directory Access Protocol, LDAP, and Active Directory. These are done outside of Hadoop, usually at the client side, or within the web server if appropriate. Kerberos is the most popular security model in today's IT environment, is an open-source network authentication protocol that lets the cluster nodes verify their identity with each other. Kerberos is a pure authentication protocol, so it doesn't manage file and directory permissions. When you implement Kerberos, users wanting access to your cluster will first contact the central Kerberos server named Key Distribution Center, which contains the credentials database. If the user-provided credentials are OK, the KDC grants access to the Hadoop cluster. To summarize, the authentication process through Kerberos has 3 steps. The authentication server grants the client seeking access to the Hadoop cluster a ticket granting ticket, TGT. The client decrypts the TGT using their credentials and, using the TGT, gets a service ticket from the ticket granting server, TGS. The TGS grants access to the Hadoop cluster. Clients use the service tickets granted by the TGS to access the Hadoop cluster. Kerberos is the most common way of securing a Hadoop cluster, through its robust user authentication mechanism. Kerberos security design involves 3 key entities. Users who want to authenticate themselves. The service to which the user is attempting to authenticate. Kerberos Security Server, Key Distribution Center or KDC, trusted by both the user and the service. It's the KDC that stores the secret keys for the users and services. 3 key Kerberos-related terms you must be familiar with, will be presented next. Realm. A realm is the basic administrative domain for authenticating users and serves to establish the boundaries for an administrative server to authenticate users, hosts, and services. Each Hadoop user is assigned to a specific domain. It's customary to specify a realm in uppercase letters. There can be multiple KDCs and, therefore, multiple realms in a single network. Principal. A principal is a user, host, or service that's part of a given realm. It's common to refer to users as user principals and principals pertaining to services as service principals. User principal names, UPNs, denote regular users. Service principal names, SPNs, are logins that are necessary to run Hadoop services or background processes and include Hadoop services such as HDFS and Yarn. Ticket. When a user wants to authenticate to a Kerberos-supported cluster, the administration server generates a ticket. This ticket contains information such as the username, usually the same as the user's principal, the service's principal, the IP address of the client and a timestamp. A ticket has a configurable maximum lifetime and a session key. Users can also renew their tickets up to a specified time. Once a user logs into a system authenticated by Kerberos, also called a Kerberized cluster, that user can continue to access all authorized services without having to authenticate again during that session. In this sense, it's similar to the familiar concept of single sign-on, SSO. In a Kerberized cluster, you can't log into your cluster with the usual user credentials. In order to log into any of the cluster nodes, you must use the cont'd utility. The cont'd utility isn't present on your server unless your server already has a Kerberos installation. If you try to use the cont'd utility without installing Kerberos, you'll receive an error. Securing Hadoop through Kerberos involves the following steps. Installing Kerberos in the Hadoop cluster. Configuring Kerberos. Setting up Kerberos for Hadoop, which involves creating the Kerberos database, the Kerberos admin user and the service principals and their key tabs. Starting up the Kerberos daemons. Configuring Hadoop for Kerberos, which involves the mapping of service principals to OS usernames and the addition of several Kerberos-related parameters to Hadoop configuration files such as HDFS site.xml and yarn site.xml. Starting up the Hadoop cluster, such as HDFS and yarn, in the secure mode and testing secure connections to the Hadoop cluster. A KDC is a Kerberos server that contains an encrypted database wherein it stores all the principal entries pertaining to users, hosts, and services, including their domain information. Besides the database, which is stored in the form of a file, a KDC also contains two important components, named the Authentication Service, AS, and the Ticket Granting Server, TGS. The AS and TGS together handle all of the authentication and access requests made to a Kerberos secured Hadoop cluster. The Kerberos database stores the principal and realm information. Once a user successfully authenticates to the AS grants ticket granting tickets to clients with which to authenticate to other services in a secure cluster. The tickets are time-limited cryptographic messages that are used by clients to authenticate with the server. The principals will then use the ticket granting ticket to request authentication and access to a Hadoop service. A key tab file is a secure file that contains the passwords of all the service principals in a domain. Each Hadoop service requires that you place a key tab file on all their hosts. When Kerberos needs to renew the ticket granting ticket for a service, it looks up the key tab file. You can create a Kerberos key tab file using the Jetty command. The ticket granting server validates a TGT passed along by a client and in turn grants a service ticket to the client so they can access a Hadoop service. It's the service ticket that enables the authenticated principal to use the services in the cluster. The scheme in this slide depicts the three-step Kerberos ticket exchange process. Once you configure authentication through Kerberos, all Hadoop services will use it. That means, all Hadoop services will authenticate themselves through Kerberos and the clients will, of course, need to authenticate as well with the KDC. Users authenticate to the name node and the resource manager services through Hadoop's RPC calls using the Simple Authentication and Security Layer, SASL, framework. Within SASL, Kerberos will act as the authentication protocol to authenticate users that need access to a Hadoop service. Three types of authorization tokens help this process: delegation tokens, job tokens, and the block access token. Delegation tokens are used to authenticate users to the name node. The name node provides the delegation token to the user once the user authenticates to the name node through Kerberos. After the user authenticates, the delegation token is shared with the resource manager, which will use this token to access HDFS resources on behalf of the user, and which also renews the token for long-running jobs. When a user submits a job to the resource manager, it creates a secret key that it shares with all the data nodes that run this MapReduce job. The job token ensures that authenticated users can access only authorized jobs and authorized directories in the local file system of the data nodes. Data nodes also use the job token for securely communicating with each other. The block access token ensures that only authorized users access HDFS data on the data nodes. Clients retrieve data from the data nodes once they receive the block IDs from the name node. The name node also issues a block access token that the client sends to the data node along with the request for the data blocks, to show that they're authenticated for the data access. Authorization answers the question, what can you do? While authentication ensures that users and services are who they claim to be, authorization ensures what users can actually do once they gain access to your system. You can deny or grant access to Hadoop data and services through the configuration of authorization policies. In a Hadoop cluster, you have several services such as HDFS and yarn, and each of these services may support a different authorization model. We will discuss authorization at the HDFS level, which constitutes the permissions users need to access files stored in HDFS. HDFS file permissions serve as an authorization check for every attempt to access an HDFS file or directory and are quite similar to those you normally use in a Linux or Unix file system. In a Kerberized cluster, a user's Kerberos credentials determine the identity of the client process. In the default mode of operation called Simple Security Mode, the user's identity is determined by the host operating system. As with a Linux file system, you assign separate file permissions for the owner of a file or directory, the members of a group and the rest of the world. You use the familiar R, W, and X permissions as in Linux, and this is how they work. R lets a user read a file and list a directory's contents. W lets a user create or delete a file or directory. X lets you access a child of a directory. HDFS supports the use of ACLS to set finer-grained permissions for specific users and groups. ACLS are a good way to go when dealing with complex file permission and access requirements and you want to grant privileges in a fine-grained manner. An ACL includes a set of ACL entries, and you can use the entries to grant or deny read and write, or execute, permission to specific users or groups. Each ACL entry has a type and a permission string as well as an optional name. By default, ACLS are disabled in HDFS. In order to use HDFS ACLS, enable them on the name node by adding a true flag property to the HDFS site.xml file. When a client connects to a Hadoop service, access is granted based on whether the user has the necessary permissions and is authorized to access the service. For example, a user may have the necessary permissions to submit a yarn job to the cluster. Service level authorization is the first access control check and comes before checking file permissions. You can enable service level authorization by setting a true flag property in the core site.xml file. Once you turn on service level authorization in your cluster, you need to configure the various Hadoop services through an ACL for each of the services. Apache Sentry provides fine-grained role-based authorization for data you store in HDFS. Sentry provides role-based authorization control, RBAC, for HDFS data. Sentry currently works with Hive and Impala. Apache Sentry is an attempt to provide a unified and consistent means of authorization across the Hadoop environment, so Hadoop administrators can specify exactly what a user is allowed to do in a Hadoop system. Sentry uses several types of privilege models to make its authorization decisions. It applies the SQL model, for example, to Hive, and the Bigtable model to HBase and Accumulo. Hadoop components such as Hive and HBase use a Sentry binding to delegate authorization decisions to Sentry. The Sentry binding applies the appropriate model for determining authorization. When users wish to perform an action such as reading a file, Sentry relies on users, groups, and privileges to authorize the user requests. Specifically, a user is any user that has access to a Hadoop component such as Hive or HBase. A group is a set of users with similar needs and privileges. A privilege in the context of Sentry consists of two components, an object and the action the user wants to perform on that object. For example, an object could be a database and the action could be a read or write operation. Once you define the logical groups that require access to specific parts of data, you can design roles to define fine-grained authorization policies, with each role specifying a set of permissions. You then assign the roles to the groups. Sentry determines authorization based on authorization policies that you configure. Two entities, a policy provider and a policy engine, work together in making authorization decisions. Policy providers store the authorization policies in a text file or in a database. Sentry uses its policy engine to check the policy provider to determine whether an action requested by a user is authorized. Sentry doesn't grant privileges directly to users. Rather, it groups a set of privileges in a role. A role can be seen as a set of privileges, such as an administrator or analyst role, for example. Users are assigned to groups and a role is always assigned to a group, not to a user. Regarding to Sentry roles, privileges, and groups, the following must be specified. A role is granted privileges. Users belong to a group. Roles are assigned to a group, never to a user. Users can belong to multiple groups. The same role can be assigned to multiple groups. Sentry uses specific privilege models for each service for which it provides authorization. Each privilege model specifies a set of privileges and a set of object types to which the privileges can be applied. The available privileges in each privilege model determine the granularity of the Sentry authorization controls. You can select the appropriate Sentry authorization policies for your environment by understanding the privilege models Sentry uses. Regarding Sentry's SQL privilege model, since that's what Sentry uses for Hive authorization, Sentry provides the select, insert and all privileges for SQL access. The SQL privilege mode is hierarchical, which means that if you grant select privileges on a table, implicitly you're also granting privileges on any view based on that table. The Sentry service is an RPC server that stores authorization metadata in an underlying relational database and provides RPC interfaces to retrieve and manipulate privileges. It supports secure access to services using Kerberos. The service serves authorization metadata from the database back storage. It does not handle actual privilege validation. The Hive, Impala, and Solr services are clients of this service and will enforce Sentry privileges when they are configured to use Sentry. The Sentry site.xml file can be used for configuring the Sentry service. When clients access Hive tables, the only controls in place are the HDFS file permissions, which aren't very strong. A user can easily make changes to the Hive metastore. There are no restrictions on a user's ability to create tables, insert data into tables or run queries based on any Hive tables. Hive authorization through Sentry allows to install fine-grained authorization policies. Although Hive uses familiar database terminology such as tables, rows, and partitions, Hive tables are in fact HDFS directories, and the partitions for a Hive table are subdirectories under the main HDFS Hive directory. You can assign various Hive privileges such as select, update, and alter to users, groups or roles, at the database or table level. However, Hive has serious deficiencies when it comes to permissions. Specifically, Hive doesn't have a built-in capability to prevent a mismatch between the metadata stored in the Hive metastore and the HDFS file permissions, since you can change the HDFS permissions directly. Hive can't limit permissions to parts of a table's data, and it also can't provide column-level permissions or define server-level roles. Sentry enables you to create roles at the server, database, and table level. You can use these roles to provide partial access to a table's data to users. A key security concern is the protection of the Hive metastore database from arbitrary changes made by clients. The purpose of Hive Server 2 is to support requests coming from clients through JDBC and ODBC user interfaces. Hive Server 2 accesses the Hive metastore to get the metadata information and also performs the necessary Hive actions for clients. Using Sentry, you can ensure that all Hive Server 2 contacts are authorized and also that users must use Hive Server 2 to work with Hive databases. In summary, when configuring Sentry authorization for Hive, you must secure both Hive Server 2 and the Hive metastore. while Kerberos authentication ensures that only authorized users and services can log in and perform actions inside the Hadoop cluster, and authorization policies control what these users and services can actually do in the cluster. You must also ensure that you can track user and service actions through appropriate auditing. Auditing is also referred to as accounting and is a key component of IT security. In a Hadoop cluster, you can track actions performed in HDFS, HBase, MapReduce, Hive, Impala, and so on. For example, HDFS audits will cover actions that read and write data to HDFS. Hadoop lets you configure audit logging of all of its components separately. HDFS has two different audit logs: HDFS audit.log for user activity and security auth HDFS.audit for service activity. Both of these logs are implemented with Apache Log4j, a common and well-known mechanism for logging in Java. The logging properties can be configured in the log4j.properties file. Hadoop logs yarn operations by users in two different log files. The Resource Manager log file includes activities performed by the Resource Manager, such as submitting application requests and allocating containers, and the Node Manager log files track events performed by each node manager involved in the yarn application, such as container requests. Data encryption is the most common way to protect key corporate data stored in a database or in HDFS. Protecting data stored in devices such as the hard drives that form the basis for HDFS storage is called the encryption of data at rest. On the other hand, protecting data on the move is called encrypting data in transit or over-the-wire encryption. Hadoop offers native HDFS encryption. You can encrypt data at the application, database, and the file system or disk level. Each of these encryption levels involves a trade-off between performance and data protection. HDFS native encryption, also called HDFS transparent encryption, is somewhere in between a database level and a file system level encryption. Encryption can be done at different layers in a traditional data management software/hardware stack. Choosing to encrypt at a given layer comes with different advantages and disadvantages. Specifically, application-level encryption. This is the most secure and most flexible approach. The application has ultimate control over what is encrypted and can precisely reflect the requirements of the user. However, writing applications to do this is hard. This is also not an option for users of existing applications that do not support encryption. Database-level encryption. Similar to application-level encryption in terms of its properties. Most database vendors offer some form of encryption. However, there can be performance issues. One example is that indexes cannot be encrypted. File system-level encryption. This option offers high performance, application transparency, and is typically easy to deploy. However, it is unable to model some application-level policies. For instance, multi-tenant applications might want to encrypt based on the end user. A database might want different encryption settings for each column stored within a single file. Disk-level encryption. Easy to deploy and high performance, but also quite inflexible. Only really protects against physical theft. Data encryption is required by a number of different government, financial, and regulatory entities. Having transparent encryption built into HDFS makes it easier for organizations to comply with various regulations. HDFS native encryption is both transparent and end-to-end. It's transparent because users don't need to make any changes to their code to encrypt data. Hadoop takes care of all the encryption and decryption work. It's also end-to-end encryption because only the client encrypts and decrypts data, without HDFS ever having to store the unencrypted data or the unencrypted data encryption keys. HDFS uses a new concept termed encryption zones to encrypt its data. Each encryption zone is an HDFS directory designed for automatic encryption and decryption of data stored in that directory. Encryption keys are stored and managed by a dedicated server called the Hadoop Key Management Server, KMS. In the context of HDFS encryption, the KMS offers three basic functionalities: providing access to stored encryption zone keys, generating new encrypted data encryption keys for storage on the name node, decrypting encrypted data encryption keys for use by HDFS clients. The scheme in this slide depicts the architecture of Hadoop's transparent data encryption. For the encryption zones and how they work with encryption keys, we have to consider the following. Each encryption zone you create has a unique encryption zone key, EZK. Each file within an encryption zone has a unique data encryption key, DEK. HDFS only handles an encrypted data encryption key, EDEK, and not the DEK. In order to read or write data, HDFS clients need to decrypt the EDEK to get the DEK for that file to read from or write data to that file. When creating a new file in an encryption zone, the name node asks the KMS to generate a new EDEK encrypted with the encryption zone's key. The EDEK is then stored persistently as part of the file's metadata on the name node. When reading a file within an encryption zone, the name node provides the client with the file's EDEK and the encryption zone key version used to encrypt the EDEK. The client then asks the KMS to decrypt the EDEK, which involves checking that the client has permission to access the encryption zone key version. Assuming that is successful, the client uses the DEK to decrypt the file's contents. All these steps for the read and write path happen automatically through interactions between the DFS client, the name node, and the KMS. Access to encrypted file data and metadata is controlled by normal HDFS file system permissions. This means that if HDFS is compromised, for example, by gaining unauthorized access to an HDFS superuser account, a malicious user only gains access to ciphertext and encrypted keys. However, since access to encryption zone keys is controlled by a separate set of permissions on the KMS and key store, this does not pose a security threat. Hadoop KMS is a cryptographic key management server and is a Java web application that runs on the Tomcat web application server that's bundled with Hadoop. KMS acts as the mediator between HDFS and its clients and the key server. KMS generates both EZKs and DEKs and decrypts the EDEKs as well. It communicates with the key server through the KeyProvider Java API. Due to the key role the KMS plays in HDFS encryption, you must run this server on a host that's separate from all the other Hadoop components. KMS lets you configure multiple instances for scalability and for high availability. In order to work with KMS for encrypting HDFS, you must configure the KMS backing KeyProvider properties in the KMS site.xml file. The KMS server can be started using the command shown in this slide. With the configuration of the KMS and the name node and HDFS clients ready, the HDFS encryption zones can be created, using the Hadoop key command first to create the encryption keys and the HDFS crypto command to create the encryption zones. Once you create an encryption zone, all files created in that zone will be encrypted. If a client needs to read a file in the encryption zone, the file needs to be decrypted. This is a typical example to create an encryption zone using the commands mentioned previously. Log in as the super user and create an encryption zone, which involves creating a new directory first and then making it an encryption zone, with the help of the create zone command option. You can check that the new encryption zone has been created with the list zones option. Finally, as the super user again, change the ownership of the zone to that of a normal user. As a normal user, encryption information from the Hello World file can be retrieved. Two other Hadoop-related security projects will be presented here. Apache Knox Gateway, usually referred to as Knox, provides perimeter security for controlling Hadoop access while adhering to your corporate security policies. Knox provides server-level authorization at the perimeter. It provides authentication and token verification at the perimeter and integrates its authentication with corporate identity management and SSO systems, letting you use identities you provision in the corporate systems to securely access the Hadoop cluster. Knox isn't a substitute for Kerberos. Knox encapsulates Kerberos and simplifies its security model by doing away with the complex client-side configuration usually required for Kerberos. Apache Ranger provides centralized administration of security policies and also provides centralized access control and auditing services. It integrates with various Hadoop components, such as HBase, HDFS, Hive, and ensures consistent coverage across the stack. Ranger consists of a policy admin server and a user group synchronization server. The admin server serves as the main interface for security administration. The synchronization server helps pull users and groups from an LDAP server such as Active Directory and stores it within the Ranger administration policy database for defining security policies for them. Finally, Ranger can be integrated with Knox. The Ranger Knox plugin enforces server-level authorization through Ranger policies by acting as the authorization provider inside the Knox gateway. This is a summary of what we have discussed in this learning unit. In order to secure your Hadoop environment, you must take care of authentication, authorization, and auditing. Kerberos is the accepted authentication solution for Hadoop. While you can use HDFS access control lists for authorization, in order to set up a policy-based authorization system, you must use something like the Sentry service. Auditing events is quite critical, and you can audit all events for Yarn and HDFS. Encryption of data is essential for securing data at rest, and Hadoop comes with built-in encryption capabilities. To complete the circle of security, you must also secure data in transit. Finally, two Hadoop-related security initiatives such as Apache No and Apache Ranger were briefly presented. This is the end of Advanced 4 Learning Unit. Thanks for watching this video.